Now, your book calls this first one the fundamental theorem of calculus part 1. Some textbooks call it part 2, and so it's horribly confusing. There are 2 parts to the fundamental theorem, and it kind of cracks me up because it's like, well, what do you mean the fundamental theorem? It's 2 entirely different things. But basically what these do is it allows us to relate integrals with derivatives. So the first part, according to your book at least, tells us that if we have a continuous function from a to b, then this function capital F of x, which is defined by the integral from a to x of f of t dt, where a is any constant, it's going to be differentiable on the closed interval from a to b, and not only that, but the derivative of this integral defined function is f at x. So basically, what we're doing here is we're saying that if we have an integral defined function and we take its derivative, we end up with the original function in the integrand. It's a little bit like, it's not entirely, because that's a little too far, but it's a little bit like these are inverse functions of one another, or one undoes the other. And again, a can be any constant at all. It doesn't matter what constant that is. And notice that we're taking the derivative with respect to x. That has to match this variable. And then we use some other variable for this, usually t, but it doesn't matter, as long as it's not x. Sometimes when students write these kind of things themselves, they have a tendency to put x here, x here, x here, x here. Everything that's a variable is x, and that's a problem. Okay? We need this to be some other variable. Now we can do all kinds of problems with this. So for example, this is the most straightforward kind. We want to take the derivative with respect to x of the integral from negative pi to x of cosine of t dt. So this is just the straightforward, exact application of the rule. We have the derivative with respect to x. We're doing the integral from some constant to x. It doesn't really matter what constant that is. This is just going to be cosine of x. Again, it does not matter as long as this function is continuous. If the function's discontinuous, we have some problems with it. So here, I mean, obviously cosine's continuous everywhere. On this one, my integrand is 1 over 1 plus t squared. That's continuous for all x, because the denominator is never 0. So that would be our only potential problem. So again, these two match. I hate it when I push that button. These two match. So the derivative is just going to be 1 over 1 plus x squared. Now, when we have a function, it's not always just a function of x. Sometimes it's a function of x squared. So if you have a function of x squared and you take its derivative, you don't need to write this, but if you're taking the derivative with respect to x of that, it's f prime of x squared times 2x, right? Because of the chain rule, which we all have finally gotten to the place where we believe in, right? So when I have something like this is not a function just of x, it's a function of x squared. Well, that means that I have to apply the chain rule. So I'm going to do the derivative, leaving the inside part, the x squared alone. This is going to be sine of x squared, and then times, because of the chain rule, the derivative of x squared, which is 2x. And we almost always write these 2x sine of x squared so that there's no confusion about what the argument is for sine. We're taking the sine of the x squared, not the sine of 2x cubed. And then we can have some that are a little bit more different. Take this one, for example. How is this one different than all the other ones we've been looking at? Yeah, the x is in the lower limit instead of the upper limit of integration. Well, can we switch these?
You could make it negative.
And make it negative. That's exactly right. So this would be the derivative with respect to x of the opposite of the integral from 7 to x of 4t cosine t dt. And honestly, in practice, almost nobody takes the time to write that down. You just go, oh, hey, I'm changing the limits of integration. I incur a negative factor. So this is going to be negative 4x cosine of x. Here's one where it gets really interesting. Now we have a variable not only in the upper limit of integration, but also in the lower limit of integration. Well, this is one where we can use one of those properties of definite integrals that we talked about yesterday. What we can do is we can break this at some arbitrary constant. Typically, I think it's easiest just mentally to divide it at 0, but it doesn't matter. So I'm going to take the derivative with respect to x of the integral from 3x to 0 of 1 over 2 plus e to the t dt plus the integral from 0 to x to the 4th of 1 over 2 plus e to the t dt. So I'm not going to take the time to do the writing that we did on this one. We realize that that's going to incur a negative factor. So this is going to be negative 1 over 2 plus e to the 3x. And then because of the chain rule, we'll multiply that times 3 plus 1 over 2 plus e to the x to the 4th times 4x cubed, again because of the chain rule. Now, if we simplify that, and I'm also going to reverse so that I just have one negative sign, you're going to see something I think that you'll find makes this faster to do. We're going to have 4x cubed over 2 plus e to the x to the 4th minus 3 over 2 plus e to the 3x. You don't actually have to take the time to split this at some arbitrary constant. Because notice, we just have, if we ignored the 3x and just did it with the x to the 4th, we would have this part. And if we ignored the x to the 4th and pretended it was a constant and had the 3x in the lower limit, we would have this part. So you're welcome not to have to write all those little steps out. You can go straight to the answer on that. Okay, so this is sometimes called the derivative part of the fundamental theorem. The second part of the fundamental theorem is one that we frankly use a lot more than this part. This first part gets used primarily when we have a function that's defined as an integral. The College Board loves those problems, right? Textbooks, not as much, but we'll do plenty of them. This second part is called the evaluation part, and we actually looked at this yesterday. We just didn't call it the fundamental theorem. So again, if f is continuous on a closed interval from a to b, and capital F is any antiderivative of f on that same interval, then the integral from a to b of f of x dx is equal to capital F of b minus capital F of a. Or, as we rewrote this yesterday, if we have the integral from a to b of f prime of x dx, that's going to be equal to f of b minus f of a. I very much like this because it tells me that the integral of a rate of change gives me the total change in whatever the quantity is. So if this happens to be velocity, this is going to give me displacement. But it can be any rate of change. And if we go on and add the f of a to the other side, we can say f of a plus the integral from a to b of f prime of x dx gives me f at b. So if I know some starting place, some initial value for my function, and I want to say, well, how much is this function at some other point, b, then I can calculate that. Again, and this reminds me real strongly of point slope, and you guys know point slope is my favorite, right? This is your starting value plus how much does it change? All right, so page 2. Up until now, when we've had something like this, where we had the integral of a polynomial function, we had to use a calculator for it. But now that we have that second part of the fundamental theorem, we can simply find an antiderivative, evaluate it at 3, minus evaluate it at -1. Typically what we'll do is find the antiderivative first. So what is a simple antiderivative of x cubed? What would that have to be?
X to the 4th over 4.
Exactly right. Well done. I typically write 1/4 x to the 4th, but you're exactly right. And what's an antiderivative of 1? X. And what we'll do is we'll put this in brackets and say we want to evaluate that from 1 to 3. That way you can do the antiderivative and then substitute in and not have to try and do both at once, which can be a little bit overwhelming to try and get all of it done at once. Especially later on when we get to some where finding the antiderivative takes a little while. So now this is 1/4 of 3 to the 4th plus 3 minus 1/4 of 1 to the 4th plus 1. If this question is on the free response of the AP exam, at that point, you put down your pencil and you go to the next problem. You do not simplify it. Because at this point, you have a true numeric answer, right? And part of what happens on these, and by the way, it won't be, right? But there may be something that has something like this where you have to evaluate a definite integral by hand. But they're not going to ask you something this straightforward. They'll ask you something like that on the multiple choice. And they're not going to leave the answer like this. So we'll practice simplifying them. But you know, on the free response, if it's a numeric answer and it's something ugly and complicated, like when we did Riemann sums, right? I told you guys, once you have the Riemann sum, if it's a free response question, stop. As soon as you have the numbers in it, don't try to simplify it completely unless you need it for a subsequent part. All right, so for this, let's see, that's going to be 81/4 plus 3 minus 1/4 minus 1. So that's going to be 80/4, which is 20, plus 2. So this is 22. And you can always check these on your calculator, right? Because you guys know how to do a definite integral on the calculator, so you can always check it.
Is it from 1 to 3, or is it from, or,
It's -1. Oh, it's -1 to 3. Thank you. So that's not going to change that, but that is going to change this. So that's going to be +1. So this is going to be 24. Yeah. And what I typically do when you have ones like this is I go ahead and distribute, and then I'll put all the ones that are fractional together and all the whole numbers together, and then see what I can do with it. All right. So this next problem is one where you'll see one similar to this. I don't remember if it's on the quiz or on the test or if it's on both. And students get hosed by this problem regularly. Okay, don't let this happen to you. And what happens is, it says find the area of the region between the curve, y equals 4 minus x squared, on the interval from -1 to 3 and the x-axis. And what happens is people partially correctly go, area. That means I'm going to need to do an integral. And what they will do is they'll just do the integral from -1 to 3 of 4 minus x squared. Unfortunately, it didn't ask for what is the value of the integral. It asked for the amount of area. And remember that if any of the curve is below the x-axis, that the integral counts that as negative. But area is never negative. So what we actually need is the integral from -1 to 3 of the absolute value of 4 minus x squared dx. Now, if this is a calculator active problem, you're good to go. You can just put that into the calculator, crank out a number, and you're off and running. But if you're having to do this by hand, and you will have to do this by hand, you got to go, all right, well, how am I going to do this? So a quick sketch of what this graph looks like. 4 minus x squared, well, that's going to be an upside down parabola or a downward facing parabola. This is 4 up here. This is going to be what, -2 and 2. And they want the area from -1 to 3. So what that means is from -1 to 2, my integral returns a positive value, but from 2 to 3, it returns a negative. And I want it to be a positive, so I'm going to multiply it by -1. So I'm going to split this integral into 2 parts. It'll be from -1 to 2 of 4 minus x squared dx. Then I'm going to take the opposite of what the integral gives me from 2 to 3 of 4 minus x squared dx. So now I simply need to take the antiderivative and apply the second part of the fundamental theorem. So it'll be 4x minus 1/3 x cubed, evaluated from -1 to 2, minus 4x minus 1/3 x cubed from 2 to 3. All right, so now we have lots of numbers to work out. So let's see, that's going to be 4 times 2 is 8, minus 2 cubed is 8, times 1/3 is 8/3, minus, at -1, that'll be -4 plus 1/3, because -1 cubed is -1 times -1/3 is positive 1/3, minus, at 3 This will be 12 minus 9. And then minus. And the nice thing is that because you're going to have two that are the same, you can just go, oh yeah, that's the 8 minus 8/3. All right, so that's 8 plus 4 is 12. Negative 8/3 minus 1/3 is negative 9/3. That's negative 3. Minus, let's see, that's going to be 3 minus 8 plus 8/3. So that's going to be 9. 3 minus 8 is negative 5, but I'm subtracting that, so it's going to be plus 5. Minus 8/3, which this doesn't come out as nicely, so I'm going to go ahead and make that 2 2/3. So it's 14 minus 2 2/3 is 11 1/3. If you had just done the integral from negative 1 to 3, because this part counts as negative, it would have been quite a bit smaller than that. All right, last example. Find the area between the curve y is equal to x cosine 2x and the x-axis over the interval from negative 2 to 4. So the area is going to be equal to the integral from negative 2 to 4 of the absolute value of x times the cosine of 2x dx. Now, do I know for sure that this curve is negative at any point? No. Do I care? No. If I slap the absolute value on that, that takes care of any problem. So, gotta wake my calculator back up. Math 9, the integral from negative 2 to 4 of the absolute value. There are several places where the absolute value is hidden in various menus. I usually just go second 0, which gives me the catalog, and absolute value is the first one that's there because they're alphabetical. So the absolute value of x cosine of 2x with respect to x, bada boom, bada bing. You're like, wow, that takes a long time. Sometimes they do when you ask them to do things that are a bit more exotic. La, 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 la. So if this is an actual test and it's taking this long, go on to the next problem and wait for this to crank out the number. There we go. 6.332 approximately. You are kind of asking it to do a lot. You're asking it to take the absolute value and you're multiplying x times the cosine of 2x on a weird sort of interval. Now, if you have one where the calculator sits there and does something like that, and it's, 3 or 4 minutes, it's probably going to crap out. You can let it keep spinning for a while, but and that generally means you have set up something that's not correct. Not always, but most of the time, if the calculator really takes a long time, you've done something wrong. Okay, any questions about that? Okay.